So, are the slides visible? Can anybody confirm? So I think you can start. First, we'll do some MCQs based on this week's lecture, and then some questions on particle size distribution. So, we have some of the MCQs first for this week. So, in the first MCQ, it is saying that in a liquid medium, the particles form aggregates due to which of these forces? What is the reason for the formation of the aggregates in a liquid medium? The first option is electrostatic forces, second is mechanical agitation, ultrasonic agitation, or a binding agent. Can you answer that? What would be the reason for formation of aggregates in a liquid medium?
Mechanical agitation.
Because we are not saying that the particles should be prevented from forming aggregates. We are saying that they are forming aggregates. What is the reason for formation of the aggregates? Basically,
Maybe binding agent.
yes, one of the option is the binding agents. For example, when you have a liquid medium and you have these particles in it, these particles have some surface charges on it, and these surface charges result in the van der Waals forces or between them, and it is also only because of the electrostatic forces that are acting on it. Every particle that you are putting through a liquid medium, this is basically a question related to DLS, which is dynamic light scattering, where you have a particle that is flowing in a liquid medium or in a solvent. So this particle has some charge on it, and because of this charge it can agglomerate with one another and form aggregates. This is mostly seen when you have a very small or finer particles. These fine particles tend to agglomerate because there is a high surface energy, and that high surface energy results in high electrostatic forces, and therefore they form aggregates. So one of the option is the electrostatic forces, and one more option is the binding agent. That is, you can make these aggregates to form if you are adding some another reagent from outside that will bind these two particles by forming certain linkages, maybe hydrogen linkages or van der Waals forces, because of the like compound that you have added from outside. So these two are the right options for this question. Next, we have the following figure depicts which category of a powder particle size distribution. You know that there are different categories for powder particle distribution because
It is
this,
a bimodal, ma'am.
yes, this is a graph that we are showing, and for this graph you have to see which is the size distribution. So what do you mean by size distribution? You have a mixture of the powder and you are trying to see what is the distribution of the particle. There are some big particles, there are some small particles, there are some medium sized particles. So you just want to draw what is the distribution of the particles. So for distribution we usually draw a frequency versus log plot, which is basically mostly a bell-shaped curve. So this bell-shaped curve can vary based on what kind of a distribution you have. So because if you have a, as you said, it is a bimodal distribution. So bimodal distribution means there are two characteristic sizes, and this is a one size and this is another size where maximum number of particles are present. Say for example, if this is 100 micrometer for example, or this is 200 micrometer, so you can say that at these two sizes you are having a maximum particle occurring in this size at 100 micron or 200 micron. So that is the right answer. The answer is bimodal distribution. The next question is, during dynamic light scattering experiment, small particles have high scattering angle, low scattering angle, several fluctuations in intensity versus time plot, both A and C. This is basically the dynamic light scattering experiment. So related to that, we have a question. So what is the right answer? Can you answer what is the right answer for this? During dynamic light scattering experiment, basically, what is a dynamic light scattering experiment? What are the like things involved in it? There is a solvent. There is a solvent, and there are particles in it. The solvent has certain particles, and you are trying to see the
Movement
particle.
of particles in
You are trying to see size distribution of the particles or a powder. So you will try to impinge a laser beam, and then you can deduct the laser or the light that is being scattered through these particles. So based on that, you can have a size distribution curve. So you have to say what was, if you have a small particles in the solvent medium actually. So what will be the happening? So for example, if you have a small and big, you might have covered this thing. So if you have something like this, you have a focusing lens, and if you have a small particle, this small particle, and if light is impinging on it, the laser light, it will scatter large angles. The small particle always scatters a large angle, but if you have a larger particle, the scattering will be small. The angles of scatter will be small, so the angle of scattering will decrease. So the right option is this: yes, for a small particle, you will have a high scattering angle. So this is in comparison to a larger particle. And also it is saying that it will have several fluctuations in intensity versus time plot. What does that mean? That means whenever you have a small particle in a solvent like this, the small particle has a higher tendency to move in the solvent. It has a higher kinetic energy, or it has a higher tendency to move randomly in the uh, solvent in comparison to a larger particle, because the larger particle does not experience a much force from the liquid to move, while a smaller particle experiences a large amount of force in a solvent to move randomly in the system. So because of its random motion, what happens, the particles are moving very rapidly throughout the medium. So always there is one plot, that is the intensity versus time plot, that is being drawn for these particles during dynamic light scattering experiments. So what you have, for example, you have an intensity versus time. You might have seen that there is these type of fluctuations are present when you have a small particle. But if you have a big particle, the fluctuations are not that frequent. The fluctuations are very frequent when you are having a small particle, because small particles have a tendency to move more randomly in this material. So there is more fluctuations and more randomness with the small particle. So yes, there will be several fluctuations in intensity with time when you are talking about small particles. So the right answer will be both A and C, that it will have a high scattering angle and it will have a several fluctuations in intensity versus time plot. So this will help you to draw a characteristic particle size distribution curve, or particle size data about the particle size, how much particles are present, of which size are present in your powder sample. So next question is, minus 125 slash plus 180 mesh powder will pass through 125
one
mesh, 50 mesh.
125 mesh.
It will pass through 125 mesh. Will it pass through 50 mesh?
Yes, ma'am. It is also passed in 50 mesh also.
Okay, so will it pass through 200 mesh?
No,
No. And 180 mesh? No. Why? Because
no.
when you're talking about this, you are actually representing, first, there are two things in this question. One is the size class. You are writing minus 125 plus 180, right? What does this mean? This means the particle is belonging to a size class which is less than 125, but it does not have a greater, it has a greater size of 180, right? So what you mean by this, you can also write it like this: 125 cross 180. The size distribution is also written like this, that it belongs to the size class 125 to 180. So this is one thing is mesh is actually when you are taking a sieve. This is a question related to sieve analysis. When you are taking a sieve, it has certain meshes on it. This mesh will decide what is the size of the particle that will pass through the mesh, right? If there are more number of meshes, then there will be smaller particles going through it. So you have to remember that if there are more meshes in a sieve, it will be inversely proportional to the particle size, for example, right? So that means if you have a large number of meshes in the sieve, that means the size that will pass through it will be small. So it will be having a smaller particle size. So one concept is mesh, which is decides what is the particle size of your material. Second thing is how you denote this mesh, because you are having, now what does this mean 125 cross 180? Because you have a stack of sieves, right? You have just sieves like this. You have C1 here, you have sieve 2, you have sieve 3, you have sieve 4. The stack of the sieves will follow certain order. That means it will have a higher mesh like number here. So there will be large mesh here, large mesh openings. I'm saying, I'm not saying large mesh numbers. I'm saying large mesh openings. That means there are large openings here, while as at the bottom there will be less mesh openings. So there will be a
That means
stack.
mesh size is low, small, ma'am.
What?
Large mesh size means mesh size is small.
Large mesh size. I'm not saying large mesh size. I'm saying large mesh openings. That means the opening of the mesh is large, right? It is directly related. I'm not saying the large mesh size. So you can write that large mesh, like larger mesh size will be here at the bottom. So you have a stack of sieves, so you have always the different sizes of the particles. So you have coarser particles at the top, you have finer particles at the bottom. So this size,
Smaller mesh to larger mesh, ma'am.
I am actually saying this is a mesh opening. I am not saying this is a mesh size. If you are getting confused, I'll write it. There's a difference between mesh opening and mesh size, right?
Yes, ma'am.
So if I am saying there is a large mesh size, what does that mean? That means the number of the meshes are large. There are more number of meshes per square area, right?
Yes, ma'am.
So that means you are talking about finer. If I'm saying it has a higher mesh number, that means it is finer. But I can also say it has a lower mesh opening. The opening is small. So you can take it as mesh number if it is confusing you. So you can write the mesh based on mesh number. So you are actually, the point is that you wanted to see what is this 125 cross 180. That means this is a sieve that has 180. The upper size sieve is 180, while as the lower sieve is 125. Right. So this C will decide the size class. So based on this question, we are having minus 125 to 180. It means that the material will pass through 125 mesh. Because it will pass through 125 mesh, it will then go to 50 mesh also. So this is the question related to sieve analysis. We have one more question which says, which of the following techniques gives the particle size distribution based on weight basis? That is, we are talking about base.
Analysis.
Sieve analysis, dynamic light scattering, optical microscopy, or scanning electron microscopy.
Sieve analysis.
Sieve analysis. So sieve analysis gives us based on distribution based on the weight, while as dynamic light scattering gives us on what parameter?
Population.
Yes, it is
Population.
population. It is optical microscopy is also based on the population, and scanning electron microscopy is based on population. Right. In the next question, we are in dynamic light scattering experiments. The particle size is dash to scattering angles. Is directly related, inversely related, unrelated, or depends on the material. This is something that we covered in the first question, that we had a small particle. What was the angle for scattering, and we had a large particle, and what was the angle of
Higher
scattering.
angle.
For smaller angle, we had a larger angle of scattering. For larger particles, we had a smaller angle of scattering, right? So that means the size of the particle and the scattering angle are inversely related, right?
Yes, ma'am.
So the answer is inversely related. So the next question is, hydrodynamic diameter is, this was a diameter that is related to DLS, right?
Diameter was clear, ma'am. Having the same transfer film.
Yes. So hydrodynamic diameter is defined for DLS, that means dynamic light scattering experiments, where we are trying to see what is the hydrodynamic diameter. This diameter is actually the diameter of the particle that is present in a medium, right? In a medium of a solvent. So we are saying this could be the actual diameter of the particle, could be anything, but we will relate it to the diameter which is called as hydrodynamic diameter. So this will have a, we are assuming that the particle is having a shape of a sphere, so that is why we are talking about diameter of a sphere, because we are assuming that this particle is having a shape of a sphere and it has some transmission particle being analyzed. So we are making an assumption that we are keeping the diffusion constant, which is the d, translation diffusion constant, we are keeping it constant for the actual particle, and for a particle, hypothetical or assumed particle which is of sphere, so for that we will determine the hydrodynamic diameter, right? So this hydrodynamic diameter actually is influenced by many factors. It will be influenced by what is your concentration of the ions in the solution. It will be influenced by your pH of the medium. It will be influenced by your surfactant additions or any changes to the solution, any electrical or dielectric changes into the solution. This hydrodynamic diameter will be influenced, right? It because based on the formula you will see that it is actually related to K T, or it was related to viscosity, it was related to D, and I think those were the factors that it was related to. So you can say that it is related to the diameter of the part, to the translation and diffusion coefficient, to the viscosity of the medium, to the temperature of the medium. So these are the factors that you can change. If you're changing the viscosity or temperature of the medium, the hydrodynamic diameter also changes. So you have to see what are the factors influencing the diameter of the particle that you are undertaking in the experiments. So the next question is, which of the following techniques is best suited to determine particle size and particle size determination? Dynamic light scattering, optical microscopy, scanning electron microscopy, both A and C. Actually, this is particle size distribution.
Both A and C you can choose, ma'am. Dynamic light scattering, yes.
Okay. Actually, we are talking about particle size because we are talking about the best suited technique. So we'll be talking about dynamic light scattering as the best size distribution, because in scanning electron microscopy, as you have read, that when you have especially finer particles, you will see when you will just have the particles that are aggregated together because of their finer size, because of their electrostatic forces, they are aggregated together. And if you are analyzing it in under a microscope, these particles will appear to you aggregated and you will not be able to distinguish the right boundaries for it, because in scanning electron microscopy basically you are trying to determine the particle size. So you will actually measure their lengths, diameters, or their dimensions of the particles. There will be a misjudgment in measuring the diameters or the dimensions of the particles. So for that, the best technique is dynamic light scattering, because there is no issues when it comes to determining the particle size distribution, especially for the aggregates. So because it is talking about being the best technique, so you will choose it as the dynamic light scattering method. Now, next question is, which morphology of the particle has the highest aspect ratio? The needle, the plate, the spherical, or a flower? This is very important, because when you will be analyzing the morphologies under the microscope, you understand that if there are different types of pre-treatments done on the powder. For example, you are processing of the powder, you are processing through mechanical milling, through atomization processes, through electrolytic depositions, through centrifugal atomization. So you will have a different morphology of the particles. So this morphology of the particles will influence your microstructure, it will influence your morphology, and subsequently it will influence your packaging, how this powder will be packaged in a like in a sinter, or before sintering, how they will be compacted or pelletized, or joined together. So this morphology is very important. So which of this morphology can you say that it has the highest aspect ratio? Aspect ratio is nothing, it is just the ratio between its two dimensions. For example, if you have a circle, the aspect ratio is balanced, right? But if you have a morphology like needle, so this needle has one larger dimension while the other dimension is very small. So this has a highest aspect ratio because the difference between the dimensions is very large. For a plate, it is also large, but there is all this comparatively better as compared to needle because this vertical dimension is a little larger. So the difference is less. For a spherical, we can say it has a equal aspect ratio, like it has both of the dimensions are almost equal. And for a flower, you have a irregular morphology, but the aspect ratio is not high. So you can say for a needle type of a morphology, the aspect ratio is very high. So basically, what I was trying to say that for a particle that is present in a liquid medium, this is related to your DLS, right? Which is related to your dynamic light scattering experiments, in which you have put a particle. Say here you have a particle, and this particle is negatively charged because I told you every particle has certain charge associated with it, and you have put it inside a liquid medium. So this charge is negatively charged. What will happen? The solvent will try to attract the oppositely charged ions towards it from the solvent. This particle will try to attract the ions of opposite charge. So there will be a positive charge on this particle. And once this positive charge will be particle, there will be a certain interface created between the solvent and the particle. And this interface is called as a double layer, where we have some charged species present, right? So this is very important in terms of your DLS experiments, because this will, for example, if you have a very highly charged particle, so it will attract large number of ions, and there will be a change in your hydrodynamic diameter, which we are expressing here. We were saying that the hydrodynamic diameter is the diameter of a sphere with the same translational coefficient, right? So if there is a difference in the charge, if the charge is increased or the charge is decreased on the particle, there will be influence on this hydrodynamic diameter. So this diameter will be changed. Once it will be changed, it will influence your results, your DLS results. So basically, if you are seeing any charged particle in a solvent, you will always see a double layer around it, as it is seen that the solid surface becomes charged due to the difference of the electronic uh, affinities, and as a result there is an electric double layer created around the particles, and this double layer will influence your hydrodynamic diameter. So based on these, we'll do certain questions after this. So we are having two types. This is what we discussed right now. We are having two types of profiles. One profile is both are intensity versus time profiles. So you have to say that there you are seeing that this intensity profile is having certain frequencies, that is the number of times that the fluctuations are happening and the number of times the fluctuations are happening in this. Obviously the number of fluctuations that are occurring in the right hand side graph are more as compared to the fluctuations that are present on the left hand side. And why are these fluctuations present? These are fluctuations coming from the solid particles in your solvent, right? This is a solvent and it has some solid particles, and once the laser is being impinged on it, it is creating a pattern on the like we are able to get a response of intensity versus time. So the question is, the higher frequency on the right would indicate dash particle. What kind of a particle is present here? This type of frequency, which is higher frequency. What could you judge from the intensity and versus time plot?
High intensity small particle.
Yes. Why small particles? Because
High
yes, high intensity. Why small particles have high intensity? The small particles have high intensities because they are more randomized, because they have a more chance to move throughout the liquid, they experience not much force from the liquid, and as such they are more random in the solution. So because of their higher frequencies, they have a higher intent, they have a have like they have very high frequencies in the intensity versus time plots, and this results in formation of this results helps us to in distinguishing between a larger particles and a smaller particles. Okay, so these are the questions that are related to your hydrodynamic diameter. So the first question says that an absorbed polymer layer projecting out into the medium will reduce the diffusion speed more than if the polymer is lying flat on the surface. So you have two types of configurations. There is a particle and it has some projections on it. If the projections are running into the medium, and in one of the cases in which the projections are lying nearly flat to the surface, and in the other case is that the projections are running into the medium, so the directions of the projections are different, or the configuration or the orientation of the projections on the surface are different. So you have to say that which configuration will result in higher diffusion. Also you can see that if you have this flat shaped morphology is present on the particle, the hydrodynamic diameter will be smaller, right? But if these projections are into the medium, because there will be a larger charge gradient now, because there will be repulsions, this repulsions will create a larger diameter, so there will be hydrodynamic diameter will increase. You can see in here and here the hydrodynamic here is smaller, while the hydrodynamic diameter here is larger, because the projections are running into the medium and they are creating repulsions into the solvent, and as such we have a higher diameter, while here we have a smaller diameter. So you have to say in which type of a configuration will have this diffusion speed will be more.
Larger diameter.
Right. So the question says an absorbed polymer layer projecting out into the medium, that is the second case, will reduce the diffusion speed more than if the polymer is lying flat on the surface. So which is the correct statement, true or false? It is saying that if in case second, the diffusion speed will be less more than in case one. This is the case one here, because this is saying projecting out into the medium. So this is case 1, so I can write here case 1. This is also case 1, and the case second is if they are lying flat on the surface. So this is case second, this is case second.
False, ma'am.
False. Why false? What is the we have a relationship between the hydrodynamic diameter and we have a relationship with the diffusional coefficient,
Yeah,
right?
KT by mu viscosity into dice.
Like we have some relationship with the diffusion coefficient, right? We have the hydrodynamic and the diffusion coefficient are inversely related.
Yes, ma'am.
So what do you say now? In case first, we are having a larger diameter. Remember, this is the case first. The one which is below is case 1. This is case 1. This is case 1 and this is case 2. So in larger diameter, the diffusion coefficient will be less. That is what the question is saying, that the absorbed polymer layer projecting out into the medium will reduce the diffusion speed more than if the polymer is lying in flat on the surface. So the answer is true. Basically, in this question, there are two things that you should know. First is if the projections are flat onto the particle or if they are projecting into the medium. So what will happen to the hydrodynamic diameter? So based on first analysis, you determine that if the projections are running into the medium, then the hydrodynamic diameter will increase. While if the projections are lying on the surface or they are encircling your particle, so the diameter will be comparatively smaller. So you first decided what is the diameter of the particle. Once you decided the diameter of influence of the projections on the diameter of the particle, the second step was to relate it to your diffusion speed, to relate it to your formula, which was the hydrodynamic diameter and the diffusion speed. So you found that it is inversely related. So for larger diameters, the diffusion speeds will be small, while as for a smaller diameters, the diffusions will be large. That is what we know. That is why we say that a smaller particle is more random in a solvent than as compared to a larger medium. So the answer is true. It says that a low concentration of ions in mediums will have higher hydrodynamic diameter. True or false? So now you have to relate your hydrodynamic diameter, which is dH, to your concentration. It is a function of the concentration of ions, right? The concentration of ions. So you do not have any direct formula that you have read, but you can understand it based on what we read here. This dilator layer. So you have to relate this double layer, the charge present on the surface of the particles and the consequent formation of the double layer with the hydrodynamic diameter. So how will you relate to it? So you have a question that says that you have a low concentration of ions in the medium. So that means if you have a low concentration of ions in the medium, that means you have the surfaces charges are less, right? So if surface charges are less, the formation of the double layer will be small, right? The double layer formation will also be less. So what will happen if the double layer formation is less? Will the hydrodynamic diameter increase or decrease? So you have to relate to the concentration of the ions, their charges, the formation of the double layer, and their consequent hydrodynamic diameter. So you can take 1 minute and then answer what could be the answer for this question. Anybody can answer that? Any answer for this?
True.
Is it true? So basically you can see the image at the back. You can see that. Can you see this is the image that we're talking about? So we are saying that if you have a particle which is having a higher concentration of the ions, the diameter will have a double layer which is very close to the particle. So as the particle has a higher concentration of the ions, there will be large amount of double layers that will be formed because there is an interaction between the double layer ions and the ions from your particle. There will be a strong attraction, and that strong attraction will result in a reduced particle. So you can see here that at low concentration of the ions, what happens that a ionic medium will produce an extended double layer, and this extended double layer will result in a larger apparent hydrodynamic, while as if you have a Higher concentration ions will mean that the electric double layer will be compressed and therefore the hydrodynamic diameter will be reduced. So for a low concentration of ions, higher hydrodynamic ion will, diameter will be present. For a smaller concentration, a smaller hydrodynamic diameter will be present. So this is a relationship of a hydrodynamic diameter with your particle morphology and with your concentration of the ions. So is it clear?
Yes, ma'am.
So now we have another question which says that DLS is useful for measurement of part.
Answer is true, ma'am. Then
Yes, his answer was true. The question is DLS is useful for measurement of particle size, particle distribution, particle shape or particle size distribution. This is what we have done. We have talked about DLS. So the DLS is useful for what measurement?
particle size and distribution.
Right. So the answer is particle size and distribution. So then we have another question which says for good wetting of the particles in solvent, which of the following is required? The concentration of surfactant should be more. The concentration of surfactant should be less than critical micellar concentration. Surfactant is not required. None of the above. See, if you want to, because we are saying that these are the charged particles that are present, present in the powder mixture. Also, because dynamic DLS is used when we are having smaller particles. So, because smaller particles will have some aggregates and there will be electrostatic attractions between the particles, and there will be hydrophobicity associated with the particles always. Whenever you take a finer particle and you try to put it in a solvent, you will always see certain hydrophobicity associated with the particles because they are tend to agglomerate with one another rather than with the solvent. So there will always be higher agglomerations. So you definitely need a surfactant in such cases. So this option is not right, that you do not require a surfactant. You will always require a surfactant, especially if you have a finer particles in a solvent. So now the question says that what is required? The concentration of the surfactant should be more. Should it be very large, or it should be less than the critical micellar concentration? What should be the answer? Anybody can answer. Basically, what we are having, we are saying that if you have you always know that what is the property of a surfactant. When you are taking a surfactant, it will try to have two ends. One will be the hydrophilic end and one will be the hydrophobic end, right? It will be having something like this. So it will have some hydrophobic end and this will be hydrophilic end. So always what will happen is this missile, there will be your particle, and around this particle, this surfactant which you have added, it will form a missile. Missile means that it form a cloud of particles. It will form a cloud like this because you have added a surfactant. The surfactant will try to wet your particle. It will try to dissolve it in the solution because it has formed certain through the chain of your hydrophobic and hydrophilic ends of the surfactant. So there will be a certain missile formation. This missile formation is the aggregate of your particle and the surfactant molecules. So if the concentration of the surfactant is very more, then it will distract your analysis because you are basically trying to analyze your particle size distribution for a powder, not for some surfactant that you have added, right? So the concentration of surfactant should always be very less. So it is roughly around 1 ml or less than 1 ml per liter of the solution. So it is very low. The concentration of your surfactant additions is always very low. So it should not be more. This option is also wrong, but this option is right. It says that the concentration of surfactant should be less than the critical micellar concentration. That means once the critical micelle formation is formed, that is not required, that because that will result in the agglomeration of the particles. So your concentration should be just lower than what it is required for formation of the micelle. So the right answer is that the concentration of the surfactant should be less than your critical micelle concentration. So this is the right answer.
Ma'am, I have one doubt.
Mm-hmm. Yes.
In atomization process, How these small particles or large particles are related to this hydrodynamic diameter.
In your atomization process, the okay. So basically, an atomization process is just a formation for your powders. So that is a method of production of your powder. That has nothing to do with your hydrodynamic diameter. Diameter or DLS is a technique to determine your particle size, shape, or like these are the characterization tools. The atomization process was basically the method for production of powders. While this hydrodynamic diameter, this is related to your technique of characterization. You are actually trying to understand how a technique like TLS helps you to characterize the powder particle, how it helps you to determine particle shape. It is just a method, or you're just reading a method of, for example, if you are reading an optical microscopy, for example, so you're reading its principle, how the optical microscopy will work. It has some lenses, it has some optical light that is passing through lenses, and then it will fall on the material. So that is a principle of the technique. This hydrodynamic diameter is also related to your principle of the technique. It has nothing to do with your process.
DLS explain particles are smaller or larger.
Yes, it will just let you know the character. It will help you in characterization of the particle, whether you have produced through
Won't
atomization or
involve in this atomization process.
come again. I didn't get that.
These DLS processes won't involve in this atomization.
No, no. This DLS process is just the method of characterizing. It has nothing to do atomization. In atomization, you are basically taking a powder to a high melting point, above its melting point, and then you are trying to impinge high gases or liquid onto the medium, and then formation of your atomized powder. That was a method to form powders. Here you are just taking the powder that you have formed after mechanical crushing, after atomization, after electrolytic precipitation, or any other method, and then you are just taking that powder and dissolving it in a solution, because in DLS you are required to pass the material through a cell which is requires a solvent medium. So you're just taking powder produced from any of those methods and dissolving it in the solvent. You have nothing doing with the atomization process. You are not trying to decrease its size. You are not trying to change its morphology. You are not trying to produce powder. You are just trying to characterize the powder. And everything that we are talking about, whether we are talking how the micelle is formed, is the surfactant added or not, how is the scattering angle influenced, this is everything done with the principle of DLS. This has nothing to do with atomization. Is it
Right.
clear?
Yes, ma'am.
Okay. So now we have one thing. This is what I was trying to show, which is you have a sample cell. In this sample cell, you are trying to put your powder, for which you are trying to characterize. So this powder is in a solvent medium. So the solvent can be anything, water, ethanol, or any organic solvent. So this medium is in the sample cell, and you are impinging the laser beam. This laser helps you to deduct the particle size distribution or particle size. So once you are forming, it is impinged on the material, you are getting a characteristic pattern of like this. This pattern is called as a speckle pattern. As you might have read that in a speckle pattern, what we have a corresponding some dark spots, these black spots. These are some dark spots, and then you can say also the white or the bright spots. So there are two spots in it. These bright and dark spots are produced because we are having a constructive and destructive interferences happening in the material. So the constructive interferences will help in creating the bright spots, while as the destructive interference will create your dark spots. So this is the pattern that what you will try to look on a detector. If you are seeing the pattern, this is the type of a pattern that you will get. If it is a static imaging, right? If the material, the powders or the sample inside your solvent is not dynamic. If it is static, then you should get a spectrum like this. This is a speckle pattern for a powder which is in a static condition. So now we'll do one question on sieve analysis. So we will do a size distribution curve. We'll try to, it is a numerical. So based on that, you will understand how the size distribution curve is made. So what some of the points that you are given is that you have a size. This is the size of your sieve. These are the stack of sieves. You can see the mesh here this is a there are large number of openings, there is a large opening here, right? So this is a larger mesh, and then there are almost very small openings at the lower sieve. So this is a stack of a sieve. So you can also see corresponding how the particles will vary. There will be a coarser particles at the top and finer particles at the bottom. So you're given a size, a stack of the sieves of certain sieves which are having certain size, 350 to 1 to 150. This is the size of the particle that will pass through the sieve. Okay, and we are saying what is the weight percentage retained on weight percentage, not weight in grams, that is retained on these sieves. So for example, you have taken a 200 grams of feed material, you are taking 200 grams, around 200 grams of your powder, and you're just putting it here in the top sieve, and then you are letting it to go for sieve shaking. After sieve shaking, you took out all the stack of the sieves and you weighed what was the powder retained on each sieve. You took one sieve, measured the weight of the powder, another sieve measured the weight of the powder, and for all sieves. So you noted down the weight of the sieves, weight of the material present on each sieve. So this is what we are talking about. So if you have a sieve, you can calculate what is percentage retained. What is retained on it is what is on top of the sieve. What will be the passing? Whatever material that you have put, some of it has retained and rest of it has passed. So the if 100 grams of the material you are putting through the sieve, that means 100 minus whatever was retained has passed through the sieve. Simple calculation. So first you have to draw a size distribution curve for this material. So for this you will try to find percentage retained. You what first you draw this table, and then you draw one more column here, and in that column you calculate what is percentage retained. You draw a column and say what is the percentage, calculate what is percentage retained. You can take 5 minutes and make one more column, and then I'll solve it for you. So you can take 5 minutes for solving it. Can anybody tell me how we will calculate the percentage retained? Say for example, for this first case, how will we calculate the percentage retained? You have to just convert the weight present given in grams to percentage.
Please explain.
So basically, you have to calculate the percentage retained on the seal. So how will you calculate the percentage? You will take 5.06 is the grams that is present on the seal, and you will divide it by the value which is the total value. That is how you do. How do you calculate your marks? You take what is the obtained marks out of the total marks. So same thing you are doing here. You are calculating the percentage retained. So you will calculate 5.06 out of how much? 204 divided by 204.27 into 100. So this will be your percentage retained for first case. Then you calculate it for second, third, fourth, fifth. Say for example, for this case, what will be the percentage retained? It will be 85.11 divided by 204.27 into 100. Is it clear?
Yes, ma'am.
So you draw a column and fill the column with the percentage retained values. Once you're done, then we'll move to the next step, because we are here to draw a particle size distribution curve. So for a particle size distribution curve, what we basically require, we are required to have cumulative passing percentage, and we are required to have particle size. This particle size we know, this is given in the question. Now we are trying to find this cumulative passing percentage. For this, first we'll calculate the percentage retained. Once you're done in calculating percentage retained, then we'll move forward. So you will get something like this, percentage retained. You can cross check what you are getting, the values that you are getting.
Yes, ma'am.
Okay, so now what we are asked cumulative passing. So first we have to find what is cumulative. You can find first cumulative retained. Okay, so you have to find a cumulative retained column. So how will you find cumulative retained? What do you mean by cumulative return? You actually mean that if you have a sieve, for example, this, you have a top sieve, which is this. So you have to say what is retained on this sieve and what is retained on this sieve in cumulative retained. Whatever was written, say for example, X grams were retained in this. And then you move to the next sieve and Y gram was retained in this or Y percentage was retained in this. So the cumulative retained will be the summation of these two for the sieve. That is, whatever has been retained earlier will be cumulated, will be added to to it. So whatever you are retaining in the previous sieves will be added to your next sieve. So this the for this sieve, for this bottom sieve, the cumulative retained will be X plus Y. Okay. So similarly, what we are trying to say for the top sieve, because there is no sieve preceding the top sieve, so the cumulative return will be same. But for the next sieve, which was below it, you will add this 2.47 with the value that is retained there, that is 2.8. You will cumulate it. You will add the previous sieve to the next sieve. So you can find a cumulative retained percentage and you will get 100 here because you are cumulating all of them. So you try to get this chart first, this table first, then we'll move forward. Have you got the answers? The cumulative retained table?
Yes, yes.
So now what we are asked to find a cumulative passing percentage. As I said, what is retained and whatever is left will be passed. So out of the total, some of it is retained and rest of it is passed through the sieve. So you will find a cumulative passing by doing what? You will use the same formula, that you will find percentage passing by 100 minus whatever is retained. So you will find the passing percentage. How? This is 100 minus 2.47, because whatever was retained, the rest of it is passed through the sieve. So 100 minus 2.47 will be 9.97.52, 94.70, 86, 75, 68, and 27. So you make a table for this and see you are getting the same answers.
Yes, ma'am.
Done. So how will you now you try to plot it in the form of a curve that you want to obtain. This was a y-axis and then you have a x-axis. You can make a rough data points for this. So this is x-axis and y-axis, right? And this was particle size. This is cumulative passing, right? Percentage cumulative passing. So what we are actually getting is for a size of 350 micrometer, okay, for a size of 350 micrometer, which is somewhere here, okay, for a size of 350 you are getting a data point of 97% passing. So this is one coordinate. You have to just plot x versus y, okay. So the next size class is 212. So for a 212 class you are having a percentage passing, which is here, this is 212. You are having a percentage passing of 94, so somewhere here. And then you are having 86 percentage passing, so somewhere here. I'm just plotting, these are the data points that I am plotting versus the particle size. So this is 75 then, and then I have 68, then somewhere 27, somewhere here. So this is the curve that I am getting. You can plot this and see if you are getting a similar curve. This is the curve that we are getting. This is the curve.
Yes, ma'am.
So now you are getting a curve which is showing you a cumulative passing and a particle size. So there is a lot of information that you can get from this curve. So one of the information that you say is, if I'm saying, because I had a particle sizes of 350 to 44 micrometer, right? So I'm saying how much percentage of the particles are less than 44 micrometer size, for example. So this is your 44 micrometer size, right? This was your data point. This 44 was corresponding to 27%. So you can say that 27% of the particles belong to a size which are less than 44 micrometer. Is it clear?
Repeat again, ma'am.
I'm saying that if you are asked that for a size, I'm defining a size for you. I'm defining that you have got the powder after your atomization and all kind of a technique. Now you are characterizing it, you are drawing a particle size distribution curve. And from this particle size distribution curve, can you tell me what is the percentage of the powder that is less than 44 micrometer size? What is the percentage of the powder that you are taking and the particles are of less than 44 micrometer size? So you can say that the particles, 27% of the particles from this graph or from this table, you can say that 27% of the particles are belonging to a size which is less than 44 micrometer. Is it clear?
Yes, ma'am.
Now, if I am saying,
The below the 44 are exactly
less than 44, because from at 44 or less than 44, because this is percentage passing, remember this is not retained, this has passed. 27% of the particles have
Okay, okay,
passed the 44 micrometer size. Okay, so now the next question is, if I'm asking now you how we define these particle size distribution curves, we define it in terms of D50 or D80. You will always read D50 or D80. What is that? That means the size of the particle. What is the particle size? This corresponds to a size of particle. That means it corresponds to x-axis. What is the size of the particle where we are obtaining 50% of the passing? That means 50% of the material has passed a certain sieve, and I have to understand what sieve is it, what is the size of the particle, right? So for example, if I am saying how you define this D50, it is a particle, it is a particle size, corresponds to a particle size. D50 means that 50% of the particles have passed that sieve. So for example, I am having this 50% here, this is a cumulative passing, 50% has passed the sieve. Now where it is cutting my curve, it is cutting here somewhere, so corresponding to that, what is the particle size? It is somewhere around, say for example, 60 micrometer for example, or it is 80 micrometer, it is written here, so it is a 80 micrometer. So you can say that 50% of the particles are larger than 80 micrometer and 50% particles are smaller than 80 micrometer. So this will give you an idea what is your distribution of the particles. Okay, so you will define D50. D50 corresponds to a particle size at which 50% of the material has passed the sieve or has passed that size class. Then also we are defining D80. So what is D80? First we will say it is a value on the x-axis. It is a value on a x-axis where 80% of the material has passed. So 80% is here, and you have to see what is its corresponding value in the particle size. So it is somewhere around 125, say for example 125 micrometers. So you can say that 80% of the material has passed the 125 micrometer size. You can say that, right? That means the particle size is less than 125 micro, 80% of the material is less than 125 micrometer.
which
Okay,
is the best one, ma'am? With the choose a D50 or D80?
it depends. There are certain nomenclatures that choose D50, some choose D80. Both are used in the nomenclatures, D50 or D80.
Mostly used as D50.
Like they will tell you by drawing a size distribution curve, they will give you they will not give you a whole size distribution curve, they will tell you this is your powder, and the value the D50 for this powder is say some micrometer, or D80 for this powder is this micrometer. So you can have an idea from that, okay, the 80% of the material is of this size, so it gives you an idea how your powder is distributed. Also sometimes this particle, because you are not, mostly what we have, this should always be a characteristic S curve, something like this, but here you are not getting a typical S curve, you are getting a slightly linear curve in some regions, because this is the experimental data. So sometimes scale of the particle size is changed. The scales of your x and y axes are changed. They are changed to log. Say the particle size will be changed to log scale. So because of that, you will have a more compressed data in a particular place. So you can get a characteristic S curve, because now you are having a dispersed curve. It is flat. It is running through a large scale, large particle size range. But if you change it to a log scale, you will have a constricted curve, and then you can have this type of a very small curve like this, which is not dispersed like this, but it is concentrated in a certain region. So some people change it to a log scale also, but that is how it will be asked. So this question is basically telling you how we are trying to distribute, how we are trying to get the particle size distribution using sieve analysis on weight basis. Is it clear?
Yes.
So I think that is all. If there is any question or any query, any questions? So okay, so that is all. Thank you.